Okay, so my name is Hannay. I'm a tech lead on the mobile infrastructure team at LinkedIn. I'm going to talk to you guys today a little bit about some of the efforts we've been making in our testing infrastructure and how we've been using Gradle to improve the consistency and reliability of our tests. So, as some of you may have heard, LinkedIn recently released Project Voyager, which was a complete rewrite from the ground up of our flagship application for Android and iOS. This was about a year-long project for some of the teams and has just recently made it out the door. In preparing for this talk, I took a look through the code base for just the Android application. We had over 140 unique committers to the project. And out of those 140, over 50 of them were what I would consider to be regular committers, meaning they were consistently checking in code throughout the development process. As you can probably imagine, if you're working on a team of that size or not working on a team of that size, you can imagine you encounter some unique problems once you begin to scale to this many people contributing to the same app. One of the big efforts that we put into Project Voyager was something we called 3x3. So the goal here was to be able to have 3 releases per day with no more than 3 hours between when you check in your code to when it's available to a member. Obviously, for native mobile applications, we can't ship to the iOS App Store and to Google Play every 3 hours. Our users would hate us. Apple doesn't review that fast, all kinds of problems. But that doesn't mean we can't be able to do that. Internally, we're shipping 3 releases a day to our employees to make sure all of our employees are always dogfooding the latest code. We're constantly getting feedback from them on every feature and bug fix that we check in. Now, in order to make this work, we need to be able to have a big focus on automation. With the previous version of our mobile apps, we released to the public every month. And whenever we were ready to release, we would cut an RC branch. We would take that build, give it to our QA team, and they would do a grueling 1-week manual regression on every single build. And that's what it would take to get to release. We wanted to eliminate the need for that entirely. We want to be able to pull a build from master branch, ship it to customers with full confidence in our automation and testing. For that, we need it to be fast, but we also need it to be reliable. So for Android in particular, we've made a big investment in Espresso and the Android testing support library, which is very convenient for us that Google's been improving that a lot this year. As we've come to find out while trying to make all this stuff reliable, UI testing is actually really hard to get reliable. One of the biggest issues we were running into was we'd have tests that would pass for the developer that wrote them, then they would check them in, another developer would pull the code, and the test would not pass. Or it wouldn't pass on the build server, so they couldn't even check in their code. They would fail the build. This is caused by a number of reasons, but a big contributing factor was that every developer was using a different type of device or emulator or Genymotion, and a practically infinite number of screen sizes, different configurations. Basically, all of these tests were running in different environments, so how could we expect them to behave the same way? This was leading to a lot of developer unhappiness and causing a lot of trouble while we were trying to get this product out the door. So we started to take a look at Gradle and say, we're already using Gradle to get consistent builds across all of our dev machines and all of our build servers. Why can't we do the same thing for tests? The way we used to run our emulators on our build machines was we had a script that was deployed to every single build machine. And that script knew how to start exactly one emulator. And that script would create that emulator from scratch every time you created a build. If you wanted any customizations, you had to make that customization to the script, roll it out to all the build machines, hope that that customization that works for your app didn't break any of LinkedIn's other apps who are also using that same emulator build script. it wasn't a great situation. And it didn't help developers locally at all. So as we started to look into this problem, we started to look at what exactly makes up an Android emulator, or Android Virtual Device as the official name, AVD. So it's primarily made up of 3 different parts. So there's the system images that ship from Google in the Android SDK. You download those once, and then you have them, and they power all of the emulators that you run for a particular API level. The second bucket of files is when you create an instance of an emulator, it generates some specific files for that emulator that contain the user data, or basically anything that's read-write, not read-only. So if we take a look into detail of what those files actually are, you'll notice on the left side here we have the files that come in the Android SDK. They contain some system image files, RAM disk files, and build properties. And then created on launch in a completely different location on the file system, we have the files that are created when you run a particular emulator instance. This is actually one thing that caused a big source of problems, because it was hard to keep the state consistent. Developers had to have the right things downloaded from the Android SDK. They had to have the right environment variables set to have the Android emulator tool look for these files in the right place. To add a further layer of complexity on top of this, the Android stock emulator supports something they call Emulator Skins. You can see in the screenshots, you're probably familiar with this if you've worked with the Android emulator. These also ship by default with the Android SDK. They're in yet another location on the file system. They're mainly made up of a bunch of PNG files and then a layout file that tells the Android emulator tool where to lay those out on the screen. By and large, most of the functions that these provide can be accomplished with keyboard shortcuts. We were also running into issues where the hardware.ini file that was included with Emulator Skins was overriding some of the configurations that we tried to start our emulator with, and that was causing some unexpected behavior or things to not run the way we were configuring them. So we just decided to cut those out entirely. Most developers actually preferred running without the skin. So to reduce our complexity, stop worrying about those. So the solution we came up with to handle this is we tried to make standalone bundles that are capable of running an emulator with as few dependencies as possible. I think we got it down to the only things we depend on are the ADB binary and the emulator binary that ship with the Android build tools. So the structure of this was pretty simple. We have a basic tar file that contains all of these user data files, and then a system directory that has the system files from the Android SDK. We created a Gradle project that runs a script on build and generates these bundles as artifacts. The script is pretty simple. It downloads the fresh system images from Google, so we don't have to depend on those files being available locally for whoever's running the script. It will also make sure the emulator that it makes has an SD card, because many developers' tests depend on that, but it is technically optional, so emulators can be created without one. And then it will actually create and run an AVD. You'll notice all of those files that are generated when you run an AVD actually take time to generate. So the second launch of an emulator will be significantly faster than the first one. So our script will start the emulator once, cache all of those files, and include them in the bundle so that the second time you start the emulator, it's significantly faster. Then the artifacts of this Gradle project are those bundles, one for each API level that we want to support. Now that's all well and good, but we also need a way to extract and run those bundles. So we created a custom Gradle plugin that has tasks for extracting and starting these out of the emulator bundles. It handles setting all the right environment variables and parameters to the Android emulator tool so that it will look for all of those files in the same location and not get messed up by whatever the user happens to have downloaded in their Android SDK or whatever they have in their home folder. It also takes care of some of the kind of flaky emulator launch details that you have to look out for when you're trying to programmatically start an emulator. It's actually somewhat difficult to tell when the emulator has actually finished booting up. Which, if you've ever tried to set up an emulator on your CI server, you may have run into this. It also can handle things like dismissing the lock screen after the emulator has booted, because sometimes it's there, sometimes it's not. We don't know. It's also capable of starting up to 16 AVDs in parallel if your hardware supports it. We have pretty beefy continuous integration machines. You're mainly limited by potentially three things: the number of cores that your machine has, the amount of RAM your machine has, and the 16 number here comes from the number of ports that ADB supports. So we try and create optimal defaults for these for what we think will give us the most stable tests. So we give a default for the amount of memory, the heap size, things like that. But we also allow users to configure these when they're starting the emulator, so that if you want something different than the default, you're able to do that, but it's not too easy to shoot yourself in the foot. Now these bundles, as you may have thought ahead, they're actually kind of big, because they involve all of the files you've downloaded from Google, plus the stuff that's created dynamically, or created on the fly. For example, the API 21 bundle is about 200 megabytes. Some of the older APIs are a little smaller, some of the new ones are a little bigger. They're about 1.6 gigabytes when you add them all up. We definitely don't want every dev's first experience with pulling the LinkedIn Android code base to be waiting for a 1.6 gigabyte download for all of these emulator images. We want them to be able to run exactly what they need and no more. So we have a custom test configuration DSL in our Gradle plugin that lets you, in your build.gradle file, specify what version of the emulator with what configuration you want to run. Then the plugin will use the project.dependencies syntax to dynamically add those dependencies at configuration time, so the developer doesn't have to deal with adding and removing dependencies to speed up their builds. Another advantage of using Gradle is we have the Gradle cache for these artifacts. So once they've downloaded once, they're available until they change. Another advantage we get from using Gradle is that since now both our bundles and our plugin are versioned artifacts. So we get all of the inherent benefits of versioned artifacts. It's become easy to change these scripts and easy to change the plugin. If we find a new optimization for emulator startup, we can make that change once and roll it out gradually, app by app, or even you can test locally. You can run on the build server with your local changes, and make sure that everything's stable before rolling it out to the entire company. Also makes it easy to roll back if you do find an issue. We also have the advantage Google will periodically update the emulator system images, and we have the ability to change the script to point to the newer image and test that out extensively before rolling that out to everyone. And it doesn't matter whether or not each individual developer has updated their Android SDK or not. So some of the results that we've seen from this, we went from a over 20-step wiki page that explained how to create, set up, start your emulator, to now we run one Gradle command. It will give you the exact same emulator that the build server runs. Your tests will run with the exact same configuration. By caching the first boot of the emulator, we've seen that now it takes approximately 30 seconds to start up an emulator, which may seem slow if you're not familiar with the emulators, but it's actually quite fast. And probably the biggest improvement, we now see the same types of test failures running both locally and on our build server. We were actually able to track down and fix a ton of our flaky tests as we were developing this, because all of a sudden we could reproduce things locally that before would only happen on the build server, where we can't see what's happening, or we don't have all of the log data, or all of the debug info that we have locally. We've also seen the failure rate of CI builds due to emulator flakiness, or the emulator wouldn't start, or it ran out of memory, or this various assortment of issues that emulators can have. That rate has dropped dramatically, and it's now actually extremely rare that we see failures due to the actual emulator itself and not due to some issue with the test. And most importantly, developers are happier. You can never make developers completely happy, but they're much more satisfied with this tool that we've built. You'll notice I didn't show a ton of code in here. We're still in the process of cleaning a lot of it up and removing dependencies on some of our internal tooling. We plan to open source this and make it available to the wider Android community. We were really shooting for today, but didn't make it, so keep on the lookout for that. Yes. So that is all I have. Do we have time for any questions? Yes. So the question is, how do we decide what the ideal emulator configuration is?
Yes. All the different emulators.
All the different ones to test on, yeah. So there's some things that are specific to your test and what you're trying to test. So screen size, for example, that can vary based on what you're trying to test. It's important that the same tests depend on the same screen size, but other than that, it doesn't have a huge impact on the reliability of the emulator. The rest of it is a lot of experimentation, and we actually talked with some Google employees, and they gave us some tips on the proper way to configure these emulators. We found, for example, using emulators with an MDPI resolution, which a lot of developers will maybe gripe about because it doesn't look quite as pretty. But it actually makes the emulator way more reliable because it's not having to render all of those pixels, and you run into out-of-memory issues much less frequently. There's a lot of things like that that we ran into. Yeah. So the question is, with the dependencies we have on the Android emulator for our testing, how many issues do we run into that would only have been caught with real devices? So we released our app at the end of November, so we're still pretty new. So far, I would say we haven't run into many issues that we couldn't have caught on the emulator. For the most part, almost all of the Android stack is the same on the emulator as it is on a real device. It's when you get down to the pretty low-level stuff that it becomes different. Some limitations that we still have in our internal testing is right now our tooling only supports Espresso tests. We don't support UI Automator yet. That's something we'll be working on going forward. And we also are interested in looking at performance testing, which is obviously something that you would want to do more on real devices than on emulators. But for right now, I'd say we're in a pretty good state. Anybody else? Cool. Well, thank you.